Our group has chosen the article entitled Chiral Metal Nanoparticle System as Heterogeneous Catalysts Beyond Homogeneous Metal Complex Catalysts for alpha-beta Unsaturated Carbonyl Compounds. The article is written by Tomohiro Yasukawa, Ai Suzuki, Hiroyuki Mamura, Kohei Nishino, and Shu Kobayashi. It is published in 2015 under the Journal of American Chemical Society. Now this is the summary of the overall project. The figure shows the overall chemical reaction involved. The alpha-beta unsaturated carbonyl compound will react to form beta-arylated products by asymmetric 1,4 addition of aryl boronic acid. This reaction is conducted with the help of heterogeneous chiral catalyst and secondary amide substituted chiraldene as a bifunctional ligand. This catalyst and ligand are chiral metal nanoparticle system. They involve in the additional reaction of aryl boronic acid to alpha-beta unsaturated carbonyl compound. The addition involved is asymmetric 1,4 addition and the process will represent a C-C bond-forming reaction. The results that obtained from the reaction are high to excellent yield products with outstanding enantioselectivity and wide substrate scope. Moreover, these catalysts were discovered to be reusable and recoverable. By using heterogeneous chiral catalysts in this reaction showed better results in term of metal and or chiral ligand recoverability and reusability, separation process and significant activities compared to homogeneous chiral catalyst. However, using heterogeneous chiral catalyst has its own limitation. The limitation of heterogeneous chiral catalyst are the lack advanced of the catalyst in the performance and scope of reaction aspect. The performance of heterogeneous chiral catalyst are poor compared to homogeneous chiral catalyst and it also has a limit scope of reaction. Thus, in this study, heterogeneous metal nanoparticle complex is used as a catalyst due to several factors such as high stability, robustness and reusability. Moreover, it also possess unique activities and selectivities as compared to reaction catalyzed by homogeneous metal complex catalyst. However, this heterogeneous metal nanoparticle complex shows limitation too as this complex limit to asymmetric hydrogenation. This may due to the difficulty of tuning natural product modifier, hence solution is being made by designing a structurally diverse artificial chiral modifier with two functionality. The artificial chiral modifier with two functionalities that newly designed and used in this reaction is dienamide chiral bifunctional ligand. This bifunctional ligand bear more than two active sites which capable it to interact with substrate. Furthermore, it also functions to generate active species and chiral environment by coordination to the surface of chiral nanoparticle. Besides, it also able to interact with the substrate to bring them close to the active centers. By bringing them closer to active centers of catalyst, it will facilitate the reaction in an intramolecular fashion. The novelty of this project is development of a secondary amide substituted chiral diene ligand. This ligand will work together with the nanoparticle catalysts to facilitate the reaction. The comparison between the previous work and current work are, in term of metal and ligand loading and, the scope reaction. Previous work need higher metal and ligand loading, and the catalysts used are limited only to the enone group compound. Meanwhile, current work shows a lower metal loading, with the wide scope of reaction. Furthermore, it also shows the outstanding enantioselectivity. The catalysts are also reusable and recoverable. The experiment starts by designing the diene ligand. Then, the ligand will develop together with the chiral rhodium silver nanoparticle system. The additional reaction will be preceded by using the developed catalysts system. Optimization of the reaction condition will be conducted to achieve the best condition for obtaining a high yield and excellent enantioselectivity. After the reaction completed, comparison will be made between the result of homogeneous and heterogeneous catalysts. Lastly, the test of recoverability and reusability of the nanoparticle catalysts will be conducted. Move on experimental results. Table 1 shows the reaction optimization with homogeneous metal complex. This reaction differs by types of ligand used. When ligand DIN4A is used, it shows high yield and excellent enantiomers compared with another ligand. Then, the same ligand DIN4A is used while changing the reaction conditions shown in entry 9, 10 and 11. From these entry, it shows that by decreasing the percentage of catalyst, the yield remain reasonable, meanwhile there is no significant loss in the enantiomer selectivity. Table 2 shows the substrate scope of reaction by using the homogeneous rhodium complex with DIN4A, which is amide substituted chiraldine. The reason why DIN4A is chosen because it shows the highest isolated percentage yield was excellent enantiomer selectivity during optimization process. Both electron-rich and electron-poor aryl boronic acids afford high yield of desired products with excellent enantiomer selectivity as shown in entry 1, 2, 3 and 5. Meanwhile, it also can be employed in furan-substituted substrate to give desired product 3E in a high yield as shown in entry 13. Furthermore, aliphatic substrate and cyclic substrate were also successfully employed in this system to give a high yield and enantiomer selectivity of desired product as shown in 3Ka, 3L, E, 3M, E and 3Ne. Table 3 is the results obtained from the asymmetric 1,4 additions in heterogeneous nanoparticles system. The table show both results obtained from the optimization reaction and substrate scope process. From the results obtained, it shows that by using ligand DIN4A will gives a high yield and excellent enantiomer selectivity as compared to another ligand. Even if the amount of catalyst used is decreased, it still shows a reasonable yield and excellent enantiomer selectivity when using ligand 4A. Meanwhile, maintaining the percentage of catalyst used and decrease the percentage of ligand in the reaction, the results obtained still showing a high yield of desired product was obtained and excellent in the enantiomer selectivity. The best optimization condition was being used during the substrate scope, and it shows that wide range of aryl boronic acids and aromatic unsaturated ester were successfully employed in the systems. As we referred to Table 4, polymer incarcerated chiral rhodium silver could be recovered and reused without significant loss of activity. To test for the reusability of the heterogeneous nanoparticle catalyst, the catalyst was filtered, washed, dried and reused. The catalyst was used 6 times in gram-scale synthesis. In all cases, high yield and outstanding enantiomer selectivities were obtained. Figure 2 shows the nonlinear effect in homogeneous metal complex system and on the heterogeneous nanoparticles system. Nonlinear effect analysis is a powerful tool to obtain the information about the structure of active species. A positive nonlinear effect was observed in the heterogeneous nanoparticles system, which mean a higher enantiomer selectivity, while linear relationship was observed in the homogeneous metal complex system. Figure 3 shows the reaction profiles between homogeneous complex and heterogeneous nanoparticles system. From the reaction profiles, homogeneous system showed a faster initial reaction rate as compared to heterogeneous nanoparticle system. When the initial concentration of homogeneous catalyst was 0.8 molar, almost quantitative yield was observed, while when the initial concentration was diluted to 0.4 molar, the reaction stopped at approximately 60%. For heterogeneous system, a long induction period was observed. Although the reaction proceeded slowly due to the longer induction period, the process could continue until almost quantitative yield was produced even when low concentration of substrate was used. This suggests that one of the factors that led to the superior performance of the heterogeneous nanoparticle system could be the stability of active species. As for the conclusion, secondary amide substituted, chiraldine modified rhodium silver nanoparticle system as a novel heterogeneous catalyst successfully developed. Besides, asymmetric 1,4 addition of aryl boronic acids to alpha-beta unsaturated carbonyl compounds successfully employed, resulting arylated products with high to excellent yields and outstanding enantiomer selectivities. The chiral rhodium-silver nanoparticle system were prepared from rhodium nanocomposites of polystyrene-based copolymers with cross-linking moieties and carbon black. The chiral ligand, which was suggested as bifunctional ligand, successfully designed. In addition, this ligand was successfully used to generate homogeneous chiral metal complex systems. Heterogeneous nanoparticle systems showed superior performance compared to homogeneous chiral metal complex systems in terms of yield, enantioselectivity and catalytic turnover. Chiral NP systems offer engineering flexibility and have the potential to be applied in many other reactions promoted by asymmetric catalysts.